You know, think back to middle school math class for a second.
Oh boy.
All right?
Yeah.
Just try to remember that specific frustration of sitting there staring at a long division problem when you already knew the answer in your head,
Oh, absolutely.
but there was always that one catch, right?
Mhm.
That mandate from the teacher where you couldn't just write the final number down.
You had to explicitly show your work.
Yes. Every single step, every borrowed 10, every remainder, just meticulously written out on the page.
It was basically the universal student grievance. I mean,
Yeah.
even if you possess the intuition to grasp the solution in like 5 seconds, the physical act of translating that intuition onto paper took 2 full minutes.
Exactly.
The system just forced a bottleneck on your natural reasoning speed.
Which is incredibly relatable today because right now, the absolute most advanced generative AI on the planet is basically stuck in that exact same middle school math class.
It really is.
When you give a modern language model a complex, multi-step problem, it takes a noticeably long time to spit out the answer. And that delay isn't because it's confused.
Right, it's not struggling with the concept.
No, it's because it's literally writing out its entire chain of thought on the screen, like word by word, token by token, before it's allowed to give you the final output.
And while forcing an AI to, think out loud is a phenomenally effective way to ensure it stays on track and arrives at the correct answer, it imposes an astronomical computational tax.
Right, the cost is just huge.
Yeah, we are spending vast amounts of electricity and server capacity just waiting for our models to narrate their internal logic.
So naturally, the question becomes, well, what if we could bypass that?
Exactly.
What if we could train the AI to be more like that rare mathematical prodigy we all knew in school? The kid who simply glances at the chalkboard, visualizes the entire problem in a split second, and arrives at the answer without writing a single English word down.
It's just instant.
Right. What if the AI could possess a hidden, instantaneous inner monologue?
Achieving that kind of invisible, instantaneous reasoning is effectively the holy grail of current AI efficiency research.
I mean, it would change everything.
It really would. If we can unlock that, the entire landscape of what computing costs and, how fast we get answers completely transforms overnight.
And that transformation is our mission for this deep dive.
Yeah.
Welcome in. Today, we are exploring the absolute bleeding edge of generative AI, looking at how researchers are trying to make models think faster and dramatically cheaper.
It's a fascinating space right now.
It is. Our focal point is a brand new, highly anticipated preprint from researchers at NYU titled Training Continuous Chain of Thought Models, A Tale of Two Regimes.
A great paper.
Yeah. We are going to explore how close we actually are to this instantaneous AI reality, the brilliant methods being tested, and honestly, the deeply surprising hurdles that are currently tripping up the smartest minds in computer science.
The stakes here really cannot be overstated. I mean, the sheer volume of compute power dedicated globally to just watching AI generate reasoning tokens is becoming a massive, unsustainable bottleneck for the entire tech industry.
So let's start right at the source of that bottleneck.
Yeah.
Because to truly understand the radical solution these NYU researchers are proposing, we first need to understand the architecture of the problem, right?
Right.
Why is it physically so demanding for a current large language model to just hand us an answer?
Well, the core issue lies in text generation mechanics. Modern LLMs achieve their impressive human-like reasoning by utilizing what we call chain of thought traces.
Okay.
They operate autoregressively, meaning they generate one piece of a word or a token, look at the entire context of what they just wrote, calculate the probability of the very next token, generate it, and then repeat that cycle all over again.
Okay, let's unpack this for a second. If I give the AI a tricky physics problem and it spends 500 words reasoning through the gravity calculations before finally giving me the number I asked for, I am essentially forcing the data center to run a massive system-wide calculation 500 separate times.
You are, yeah. Every single one of those 500 thinking tokens requires a full pass through the model's billions of parameters.
Wow.
It is a discrete, sequential process. You are paying for the compute of all 500 steps, even though the only thing you actually wanted was the final answer at the very end. The text generation itself is the anchor dragging down the speed.
Which brings us to the core premise of this new paper, right? The pursuit of continuous chain of thought, or continuous co-supervision.
Exactly.
The researcher's goal is to entirely replace those verbose, wordy reasoning traces with a highly compressed sequence of dense latent representations. In plain terms, they want the AI to reason without using discrete English words at all.
What's fascinating here is why this specific approach matters so much. The mechanism they are tapping into is the model's latent space.
Right, the latent space.
Yeah. Latent space isn't made of words. It's a high-dimensional mathematical landscape where the AI natively maps and understands concepts. Words are merely the translation layer the AI uses to communicate with us.
So it doesn't actually think in English.
No, not at all. By bypassing the need to constantly translate its internal mathematical state into English tokens, which were designed for human communication, not rapid machine calculation, the AI can theoretically process incredibly complex logic in its pure native state. The reduction in inference compute would be staggering.
Okay, here's where I have to throw a flag on the play, though.
Go for it.
If the AI is no longer using words to think and everything happens in this invisible mathematical space, how on earth do the researchers supervise it?
That is the million-dollar question.
Right. Like, we can't grade a math test if the student's work is completely invisible. If you can't see the steps the AI is taking in its head, how do you reward it for good logic or penalize it for bad logic during training?
That invisible grading problem is the central friction point of the entire field right now. It has effectively split the AI research community into two rival philosophical camps, which the paper refers to as the two regimes.
The tale of two regimes?
Exactly. Everyone agrees on the goal, but they vehemently disagree on how to solve the invisible supervision issue.
So if we are flying blind on the grading, I imagine you essentially have two choices. You either have to look at the final answer and try to work backward to figure out if the hidden thoughts were useful, or, I don't know, you try to force the model to guess the entire hidden chunk of logic all at once based on past examples.
Your intuition is remarkably close to the two actual methodologies.
Oh, nice.
Yeah, so the first camp utilizes what is called indirect supervision. You will see research papers in this camp with names like Cody or Coconut.
Coconut, I love that.
Yeah, AI researchers love their acronyms. Their approach is to take the model's own final layer activation, the mathematical state, right before it spits out an answer, and feed it back into itself in a recurrent loop.
Okay, so it loops.
Right. The model is essentially tasked with compressing long, wordy, chain-of-thought trajectories into a very small, fixed number of latent vectors by evaluating the final outcome.
Wait, so the researchers aren't explicitly telling the hidden layers what to think at step 3 or step 4. They are just setting a constraint like, hey, you only get 6 invisible thoughts, and letting the model's neural network figure out the best way to compress the logic to reach the correct final answer.
Precisely. The model iteratively learns what mathematical representations are useful by seeing if the final answer works out.
That seems smart.
It is, but this method harbors a massive logistical drawback. Because it relies on sequential autoregressive passes during the training phase itself, feeding that loop over and over, waiting for step 1 to finish before evaluating step 2, the training process is excruciatingly slow and computationally heavy.
Which opens the door for the second camp, right? The rival regime, direct supervision.
It is, exactly.
This includes earlier methods like color, and that's where our NYU researchers introduced their big breakthrough, a method they call CMTP.
Right. Direct supervision fundamentally alters the training architecture. Instead of waiting for recurrent loops, it maps predictions straight through the embedding table and operates over variable length traces using a technique known as teacher forcing.
Teacher forcing, okay.
The monumental advantage here is parallel training. Researchers do not have to wait for step 1 to finish to train step 2. They can calculate the loss and train the entire sequence simultaneously, making the training phase vastly faster and cheaper.
And the specific flavor of direct supervision introduced in this paper, CMTP, stands for Continuous Chain of Thought via Multi-Token Prediction.
Right.
Instead of doing the slow loops, it takes a span of text from the training data, say a chunk of 4 consecutive words from a successful reasoning trace. It mathematically averages their embeddings together and then trains the model to predict the multiple tokens that make up that latent space all at the same exact time.
Yeah, by utilizing a small neural network layer, it projects the hidden state into multiple token representations concurrently. It is a highly aggressive way to simulate that latent reasoning without the sequential wait times.
Okay, wait, I need to pause on that averaging concept for a second.
Sure.
So CMTP is taking a chunk of 4 distinct, specific words, throwing them into a mathematical blender, and averaging them out into one single data point.
Essentially, yes.
Doesn't that fundamentally destroy the logic?
Yeah.
Like if I average the words divide by 2, and now I just get a blurry conceptual smoothie where the precise instruction gets totally lost, How does a blended smoothie of words retain enough sharp logic to solve a rigorous math problem?
The blurry smoothie concern is the exact vulnerability the researchers wanted to probe. To determine if direct supervision could handle precise logic without losing its meaning in the blender, they set up a rigorous head-to-head collision between the two regimes.
Okay, let's look at the tape from this first matchup. They put both methods to the test using a dataset called GSM-8K BOG. And this is pure, highly structured mathematical expressions. We are talking equations stripped down to their absolute bones. No natural language filler, just compact lines like, bracket 18.5 minus 8.5 equals 10, close bracket.
It's the ultimate test of rigid logic.
Yeah.
And the results defied the initial intuition about losing precision.
Oh, really?
Yeah. The smoothie approach, CMTP, shined brilliantly. It didn't just survive the pure math test, it matched or outright outperformed the meticulous step-by-step indirect methods like Cody.
Wow. And it wasn't just accurate, it was remarkably efficient to train, too, right? I recall the paper noting that older direct methods like Coder required around 50 epochs, meaning 50 full, exhausting passes through the entire training dataset just to converge and learn the task.
Exactly.
But CMTP figured it out and converged in roughly 5 epochs.
A tenfold reduction in training cycles is a massive speed-up. Furthermore, because CMTP trains in parallel rather than sequentially, it proved to be roughly 2 times faster than Cody in pure wall clock time.
That's huge.
But perhaps its most impressive feat emerged during a stress test of sample efficiency. When researchers drastically restricted the training data to a low data regime of just 12,000 samples, CMTP consistently maintained its lead over the indirect Cody method.
So we have to ask why, right? How does a method that mathematically averages chunks of tokens together beat a method that carefully, indirectly compresses logic step by step, especially on pure math?
The researchers conducted an autopsy on the dataset itself and uncovered a critical structural secret. It turns out that pure structured math datasets like GSM-8K-OG are highly repetitive.
Oh, really?
Yeah. Approximately 50% of the training samples in that dataset actually boil down to just 100 distinct problem structures.
Ah. Okay, so the meticulous step-by-step method, Cody, wasn't necessarily learning how to do math better, it was just overfitting.
Bingo.
It was essentially memorizing the rigid format of those 100 structures because it trained sequentially on them over and over. Meanwhile, CMTP's multi-token averaging forced it to learn the underlying mathematical concepts rather than just the formatting.
The empirical evidence strongly points to that conclusion. Because indirect methods train in those recurrent loops, they become severely over-indexed on specific, repetitive structural patterns.
That makes total sense.
Yeah, and when the researchers presented the models with held-out, completely unseen mathematical problem structures, Cody's accuracy dropped substantially. It didn't know how to handle the novelty. CMTP, conversely, generalized beautifully. Its direct alignment with the basic pre-training objective of the underlying language model made its latent representations far more robust for purely structured data.
Okay, so the direct blender method is a massive success for pure, rigid math. But human reasoning isn't just numbers and brackets.
Right.
We use words, we explain things, we add context. If you feed this highly efficient, mathematically aligned model a word problem that actually mimics human speech, does it still hold up?
The researchers anticipated that exact question, which leads to the second major experiment in the paper.
Yeah.
They transitioned to a data set called GSM-8K-OG-NL. The NL stands for natural language.
And the traces in this data set look very different. They're about 2.5 times longer than the pure math ones, averaging around 70 reasoning steps. And they are packed with verbose, sentence-per-step explanations.
Exactly.
Like, instead of seeing a clean 18 times 12 equals 2 at 16, the training data forces the model to process. Bella initially had 18 packs times 12 chocolates per pack equals 216 chocolates.
The introduction of natural language triggered a major plot twist in the data. Suddenly, the indirect supervision method, Cody, vastly outperformed the direct supervision method, CMTP.
Wait, really?
Yeah, the performance gap was stark. Cody achieved an average accuracy of 47.82% using an incredibly tight budget of just 6 latent steps. CMTP, despite utilizing a much wider reasoning runway of roughly 34 steps, struggled to hit 43.49%.
So the method that thrived on pure math completely stumbled the moment Bella and her chocolate showed up. Why does adding conversational context cause the CMTP model to lose its edge?
The failure point lies in how the two regimes handle filler. Indirect methods, by their very nature, thrive on harsh compression. When you constrain Cody to a fixed budget of only 6 latent invisible steps, it is mathematically forced to become ruthless.
Ruthless how?
It discards all the conversational fluff, it throws away Bella initially had and chocolates per pack, and distills the latent space down to only the core mathematical logic necessary to reach the final answer.
It naturally filters the noise because it just doesn't have the space to keep it.
Exactly that. But direct methods like CMTP operate differently. They don't have that fixed bottleneck. Because they use teacher forcing to map to the embeddings, they are actively trying to predict the full verbose trace from the training data.
Oh, I see.
Yeah, they're spending computational energy trying to accurately predict the filler words along with the math.
You know, the irony here is incredible. We spent the last 5 years of computer science trying to make AI sound conversational, friendly, and human. We wanted it to explain things to us like a tutor. But beneath the hood, those human filler words are the exact variables sabotaging the AI's ability to think efficiently. It's like trying to do complex calculus in your head while someone is standing next to you making small talk about their trip to the candy store. The context is actively distracting the calculation.
The distraction is palpable. And computationally, it initiates a devastating chain reaction known as error accumulation. This brings us back to the concept of teacher forcing used in direct supervision.
Let's break down teacher forcing because it sounds like a helpful thing, but it's actually the trap.
It really is.
So teacher forcing is essentially like learning to drive a car with a highly advanced GPS that instantly recalculates and physically bumps your steering wheel the millisecond you start to veer off path.
That's a great way to think about it.
Right, and during practice, you feel like an amazing driver because the system never lets you fail. You're constantly forced back to the perfect route. But during the real test, what we call inference, the GPS is turned off.
You are totally on your own.
Exactly. You are driving entirely on your own. And if you make one slightly wrong turn early on, you have absolutely no idea how to get back on track because you never learned how to recover from a mistake. You just end up in the wrong state entirely.
That driving analogy captures the train test mismatch perfectly. During training, CMTP is fed the correct next chunk of tokens no matter what. But during inference, the model is conditioning its next thought purely on its own previous thoughts.
Which is dangerous.
Very. The paper highlights a wild, fatal example of this error accumulation. Because CMTP uses span prediction to guess chunks of tokens, it will occasionally hallucinate an extra token in the middle of a verbose sentence. It will output something mathematically absurd, like predicting 3 times 2 equals 6.67.
Ouch, yeah, that's bad.
And because the GPS is turned off, the model accepts that hallucination as absolute truth. It bases its next logical step on the false premise that 3 times 2 is 6.67. The entire reasoning chain violently collapses. A single erroneous token cascading through the generation guarantees a failed final answer. Therefore, in the presence of verbose, natural language, the indirect method's ability to ruthlessly compress the noise and ignore the fluff makes it the definitive winner.
Okay, so let's look at the scoreboard so far. Direct supervision and multi-token averaging win the day on pure, structured math by avoiding overfitting.
Correct.
Indirect supervision and recurrent loops win the day on wordy, semi-natural math by filtering out human noise. So the obvious next question for the NYU researchers was, well, what happens when these models face a truly realistic, highly complex scenario that blends both deep math and complex language?
This is where the paper delivers its most sobering and arguably its most important reality check for the industry. They moved away from the simplified GSM-8K datasets and tested the models on the math dataset.
And the math dataset is a whole different beast. These are highly complex tasks with incredibly realistic, messy reasoning traces generated by off-the-shelf, powerful LLMs. We are talking about reasoning traces that average over 350 tokens long.
Yeah, it's intense.
This is real-world, enterprise-level complexity.
And when subjected to that level of real-world complexity, both regimes, direct and indirect, experienced a total systemic collapse.
Wait, total collapse. Like, neither method survived the jump in complexity.
The drop in performance is staggering. Let's look at the baseline numbers using the Quinn model architecture. When researchers allow the model to use standard chain of thought, the slow, tedious, word-by-word generation we currently use, it hits a respectable 53% accuracy on these incredibly complex problems.
Okay, 53%.
But the moment they applied the continuous chain of thought methods, whether it was the direct CMTP or the indirect CODIA, the accuracy plummeted to a dismal range of between 7% and 15%.
From over half right to practically guessing, that is a bloodbath.
A total bloodbath. The stark conclusion drawn by the researchers is that the simplified benchmarks currently dominating AI evaluations are creating a mirage. Datasets like GSM-8K are actually overstating the practical, real-world utility of continuous coding methods.
That's a huge reality check.
It is. As it stands today, neither the direct nor the indirect method alone is robust enough for prime time in realistic, messy, long-form settings.
Here's where it gets really interesting to me, because it highlights a classic trap in technological development. It's like we train these autonomous AI models on a highly predictable, perfectly paved driving simulator.
Right.
On the test track, they perform beautifully, they corner perfectly. Yeah. But the moment we drop those same models into the chaotic, unpredictable, pedestrian-filled traffic of New York City, they immediately crash into a hot dog stand.
Completely.
The simulator gave the researchers a false sense of security regarding how far the technology had actually progressed.
The New York City traffic analogy is incredibly apt. The real world of logical reasoning is loud, verbose, and structurally unpredictable. If we connect the findings of this paper to the bigger picture of AI development, the researchers assert that the future of fast, invisible AI reasoning isn't going to be a victory for one regime over the other.
It has to be both.
Exactly. The path forward dictates the necessity of hybrid models.
Let's explore what a hybrid model actually looks like in practice. How do you combine a blender and a compressor?
The prevailing theory is that we need models capable of adaptively switching their reasoning pathways based on the specific demands of the prompt.
Oh, that makes sense.
Yeah, we need an architecture that utilizes hidden, latent reasoning, perhaps leveraging CMTP for the easy, highly structured, compressible arithmetic. But then it needs a mechanism to detect when the logic becomes too complex or too verbose and seamlessly fall back into discrete token-based reasoning for the precise, fragile logic where error accumulation would be fatal.
So, to go back to our middle schooler, we need an AI that intrinsically knows when it's safe to visualize the answer instantly in its head, and when the problem is so complex that it needs to physically pull out a piece of paper and carefully show its work to avoid making a silly mistake.
Exactly, that kind of dynamic cognitive pacing. Direct supervision provides the training, efficiency, and mathematical alignment, while indirect supervision provides the ruthless compression needed to manage long, distracting context windows.
Right.
Future breakthroughs in continuous copy will almost certainly require integrating their respective strengths into a single unified architecture.
All right, let's bring all of this cutting-edge research home for you listening. Why should you, in your day-to-day life, care about latent vectors, teacher forcing, and the failures on the math data set?
It affects everything.
It really does. Because the next time you boot up a cutting-edge AI, whether you are using it to draft a complex legal strategy, debug thousands of lines of code, or analyze financial data, and you notice that brief, agonizing pause where the cursor blinks as the model thinks before it types, you are witnessing the absolute frontier of computer science trying to optimize global compute power.
The energy grid demands and the raw financial costs associated with these massive data centers spelling out their internal thoughts token by token are astronomical, and frankly, they're unsustainable at a global scale.
If researchers at NYU and beyond can actually perfect this true invisible inner monologue for AI, it would save billions of dollars in compute costs globally. You would receive instant, profound answers to the most complex questions imaginable without any waiting.
That's the dream.
But as this deep dive into the latest SOTA research shows, we are still fighting the fundamental, unyielding mathematics required to get there. We're still trying to teach a machine how to hold a complex 350-token thought in its head without losing the plot entirely.
And that technological struggle leaves us with a critical, almost philosophical question for the trajectory of artificial intelligence.
What's that?
Well, the ultimate stated goal of continuous chain of thought is to engineer an AI that reasons entirely in dense, continuous mathematical vectors. That is a native language that human beings literally cannot read, visualize, or interpret.
It's totally alien to us.
Right. If researchers fully succeed in this endeavor, we will absolutely get our incredibly fast, incredibly cheap answers. But we will simultaneously lose the ability to look under the hood and verify how the AI reached its conclusion. Its internal reasoning process will become an impenetrable black box.
We all want the math prodigy's breathtaking speed. But when it comes to systems making medical, legal, or strategic decisions, maybe we still really need the ability to review their work. Are we ultimately willing to sacrifice transparency and interpretability just to make the machine think faster and cheaper? It is a profound trade-off that the tech industry and all of us using these tools are going to have to navigate very, very soon. Something to mull over the next time you are waiting on a loading screen. Thanks for taking this deep dive with us.